The quadratic formula. We'll derive it later, along with lots of other good stuff. First, let's use it to solve a second-order polynomial. A quadratic equation like this one. Say it with me. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And that become this, and then that, meaning x equals negative 2 or negative 3. Next, we'll plug these back into the equation to see if they work, and they do. A few more examples. Plus 5x becomes minus 5x, and as you can see, we are moving much too quickly. From positive 6 to negative 6, one more example. From positive x to negative x, good enough. But where did the quadratic formula come from? Before we tackle that, we return to this, which can also be solved through factoring. Either the parentheses on the right or the parentheses on the left must be 0. That fact gives us back our solutions. Or think of it as length times width, an area. See that? X squared plus 5x plus 6 is an area. And this area, so you're telling me, equals 0. Okay, but what if it didn't equal 0? What if we let x squared plus 5x plus 6 equal anything? Why not? Then we could graph it, a parabola, with these roots. Another one, same shape but a different location, different roots, and a third and a fourth. They are all the same shape because I chose to let a equal 1 for all of them. If it was 8x squared instead of just x squared, if it was 8x squared, you'd have a skinnier parabola, and we'll zoom in on this one to derive an equation for the vertex. I promise we're getting back to the quadratic formula in a second, but this is good practice for that derivation. Anyway, this is the equation we're excited about, especially if or when both sides equal 0, which happens here at the vertex. And if this is still our parabola, its coordinates are, wait for it, 1/2 and negative 6.25. But what the devil are those? It's the focus, a point, and the directrix, a line, famous for this. Take any point on the parabola, such as that one. The distance from this location to the focus equals the distance from this point to the directrix. Yep, we're dropping a perpendicular. And as you can see, it works out. Each line here is 6 green tabs long. Real quick now, we go general, formulas revealed, and the point is xy. No, the point is x and ax squared plus bx plus c. But we're focused, get it? We're focused on lengths, which would be the same in any coordinate grid. So we'll choose this one, where b and c are both 0. Told you guys that b and c don't affect the parabola shape, and if a equals 1, the vertex, directrix, and focus are such and such. And we are ready to prove stuff. B and C are still 0. And finally, the quadratic formula. Finally, remember that? Time to derive it. Subtract, divide, now add. But what do we add? Well, let's add something clever. Because using something we know about squaring binomials, we can turn this into that. And we are on our way. Pausing again for something that we'll come back to, because it's all about algebra now. Behold the quadratic formula. Okay, let's back up to that earlier result. You can call this a new approach to an old problem. This time we need to take the square root of 6.25. Do you know what that is? Plus or minus 2.5. And that gives us the same answer we got before. Nice. But if you are still squirrely about that square root of 6.25, we can draw it out. See, 2.5 on each side. The area is 4, 5, 6, and a quarter. Now look up, because this says basically the same thing, only it's a bit more interesting. And this, apparently, equals that. Neat. And mysterious, because these two pieces cancel out. So here's the question. How can the remaining area on the left be negative? Positive x's and b's and a's on the left, negative c over a on the right. How can that be? Well, I'll tell you. It's because a, b, c, and x cannot all be positive. Remember this equation, both roots were negative. In this equation, b is negative. The areas are eating into each other. And all I'm saying is that in each of our 4 examples, there was some mix of negative a's, b's, c's, and x's. because we can't have this area be less than 0, which, with a bit more algebra, is a pictorial argument for this constraint on the quadratic formula, which can seem a little bit arbitrary. No negatives allowed inside the square root. So maybe that makes some more sense, and this requirement was met by all 4 of our earlier examples, but it is not met here. This equation is a rule breaker. 1 squared is not greater than 24. It's a rule breaker, but it's also just a parabola. The only issue here is that we have no roots on this graph. Bummer. Neither does this parabola, and I'd prefer to talk about this one because apparently this equation has no solutions. Or does it? We'll find out, but first we'll give it a tweak. I hope that's okay. You'll see why later. Back to the future with, say it with me, negative b plus or minus the square root of b squared minus 4ac all over 2a, and the square root of negative 25 is 5i plus or minus 5i. Great. 2 complex solutions, which is just what the fundamental theory of algebra demands, but to finish up, we'll focus on this solution, and notice that this becomes that. Yikes. But pictorially, these 2 cancel out those 2, leaving us this, and algebraically speaking, we can rearrange to find one last time something that you might recognize.